Sometimes our systems of differential equations just don't cooperate to be homogeneous, so we need to solve non-homogeneous systems of linear first-order differential equations as well. We're going to talk about one method, one option of how we can solve those. Remember, the general form for a solution to a non-homogeneous linear system of first-order differential equations is x equals xc plus xp, where xc is the general solution to the associated homogeneous linear system, and xp is a particular solution to the non-homogeneous system. So let's take a look at using the method of undetermined coefficients to solve a system of linear first-order differential equations that are non-homogeneous. So my system's going to be the derivative equals negative 1, 2, negative 1, 1 times x plus negative 8, 3. Remember, the homogeneous version would just not have that negative 8, 3 there. Those would be zeros. Where non-homogeneous, we add something that's not 0 to it. So the first thing we have to do is we're going to solve the associated homogeneous system, which, like I said, would be x prime equals negative 1, 2, negative 1, 1, x. Well, luckily we already know how to do that. We need to find our eigenvalues, and then we use the eigenvalues that we found to find eigenvectors that are associated with them. This one, in fact, ends up with complex eigenvalues, so then we put them into a real form, and when we solve them, we do all of this, we end up with xc, our solution to this associated homogeneous system. If you want to see examples of homogeneous systems solving, so how we go about all of this, take a look at the homogeneous linear systems video and you'll see those. For the sake of this video, I'm going to skip those steps for time. All right, so we get our xc is going to equal c1 times cosine t plus sine t. And then our second entry is cosine t. And then we'll have plus c2 times cosine t minus sine t, and negative sine t as the second entry. And you can see, of course, signs that this did have complex eigenvalues by these sines and cosines being introduced into our solution. So now, since our vector f here, f is negative 8, 3, it's constant, well, this means that our particular solution, it's probably going to equal a constant vector too, because remember, this is going to solve our associated homogeneous system. We just solved all this. So it's really, this next part is all about dealing with this negative 8, 3 part. So our particular solution that we're going to be working with should look like constants. So it's going to look like a constant vector also. We'll call it A1, B1. Now you're right, remember that when we were doing undetermined coefficients before with higher order differential equations, we basically just assume that this is a solution, plug it in, and then solve for what those constants A1 and B1 must be. So it works the same with systems. So if xp is going to be that, it's going to be the solution that we plug in. We also need to know what the derivative of it is. So the derivative of constants is zeros, and the way we take a derivative of a vector is take a derivative of each entry in the vector. So we have the derivative of a constant and a derivative of a constant, so zeros and zeros. And then we're going to plug these things in and say, hey, they were solutions, great, let's take a look at what they give us. So we've got x prime, or 0, 0, equals a, negative 1, 2, negative 1, 1, times x, that was a1, b1, and plus negative 8, 3. So let's do some multiplying, combining. Remember, to multiply a matrix, you go across the row, you go down the column, and you put it where it belongs. So you've got 0, 0 as our column vector that we start off with still. And then we'll go across the row, negative 1 times a1, top left times the top, takes us to have negative a1. Then going to the right, I have 2, going down I have b1, so this will be plus 2 b1, and that's my first row because I used the first row of the matrix to get it. So to get the second row of the matrix, I need to use the second row of the matrix. We'll start with on the left with negative 1, multiplying it times the top a1, we have negative a1, and then adding to that, we have 1 times b1, the right times the bottom, so it's 1 times b1 is 1 b1, and that concludes that multiplication. Then we're going to have to add negative 8, 3. So now let's add these two vectors together I have on the right hand side. So we'll leave 0, 0 on the left for now, and adding them across, we just add top row to top row. So we'll have negative a1 plus 2b1, negative 8 or minus 8, negative a1 plus b1 plus 3. And now for these two vectors to be equal to each other, the rows in them must agree. So to top row on the left gives me 0. The top row on the right gives me negative a1 plus 2b1 minus 8. And the bottom row on the left gives me 0. On the right gives me negative a1 plus b1 plus 3. And now I have to solve for one of these and then for the other. So I have a system of equations, two unknowns, two equations, and so I can solve. I'm going to solve the second one first. I'll solve it for a1. It's going to give me a1 equals b1 plus 3, and then I'm going to plug that into the second one, which is going to give me negative b1 plus 3 plus 2b1 minus 8. All that's equal to 0. Then I have to solve for b1, so I'll distribute that negative. I'll get 0 equals negative b1 minus 3 plus 2b1 minus 8. Combining like terms, I've got b1 minus 11 is equal to 0. Adding 11, I get 11 is b1. And then plugging that back into this second equation, I get a1 equals 11 plus 3. So a1 is going to equal 14. And remember, we assumed that xp was a1, b1 and made all of this magic happen. So what we have now is we know xp is going to equal 14, 11. Now remember, our total solution looks like x equals xc, which we've kind of tabled, but it was c1 times cosine t plus sine t with our second entry of cosine t plus c2 times cosine t minus sine t, and minus sine t as the second entry, and then plus p, or plus xp, x sub p, and we found that now, so that is plus 14, 11. And that's our general solution to our non-homogeneous differential equation.